begin by sort of reviewing what's going on for the rest of the month. For Monday, we're going to start on Chapter 6, which is the bioelectricity chapter. We'll spend quite a bit of time on that chapter. So start reading. The sections I suggest are 1, 6, and 10. The first, say, 10 sections of that chapter are really sort of a review of electricity that you might pick up from an introductory class. So feel free to read the whole review, but I'm going to basically assume you're familiar with some of the basic ideas of electricity, and we're going to focus on the biomedical applications. If you have homework number 4 is due today. If you haven't handed it in yet, bring it up after class and stick it in the envelope. Homework number 5 is due a week from today, and we talked about some of those problems last class, and we'll talk about a few more today. And then finally, homework number 6 is going to be due Friday, October 25th. And the second exam will be the very last day, October 30th, on Wednesday, October 30th, over chapters 4 to 6. So that takes us through the end of October. So that's the game plan. And today we're going to finish up on chapter 5. And the first thing I want to do is talk a little bit about one of the homework problems that I didn't mention last class. That's problem 5.8, which is in the homework. So I'll just give you some hints. It has to do with osmotic pressure in cartilage. So this is a sort of a well-known example of when you would, when osmotic pressure is important. You have cartilage is at the end of bone. So here's a bone, and so this is the bone here. And then there's a layer of cartilage on top of it, and then this is the extracellular fluid or whatever is surrounding. Maybe it's another bone interacting with it, but we'll just imagine it's some extracellular fluid. This layer is maybe a millimeter thick, okay, maybe a couple millimeters, and it's made mostly of these thin fibers, which are kind of going in random directions, called collagen. Collagen fibers. But there's something else that's in cartilage that besides those fibers, and there's these molecules called proteoglycans. So these are proteoglycans, and these molecules are fixed. They're attached to the collagen matrix, and they're charged. They have a negative charge, and therefore they attract sodium ions. They attach the positive ions in here in order to balance the charge. So you get a lot of proteoglycans and you get a lot of surrounding sodium ions. Now, with all this stuff in here, with these big proteoglycans and the sodium ions, especially the sodium ions since they're free to move, you basically get osmotic pressure. You get a large osmotic pressure that's sucking water into the cartilage. So the thing about collagen fibers is they can exert tensions, but they can't exert compressions. So the reason why this cartilage even works is because the water gets sucked in and kind of pumps up the cartilage so that it's sort of like an expanded balloon held there by osmotic pressure. So then if you have another bone or another bone that makes contact, if you kind of push it down and up, it's got this layer of water basically trapped there by osmotic pressure to keep the bones from scraping and damaging them. So this problem asks you to imagine an experiment. Suppose you wanted to do an experiment to understand this. What you could do is you can put another type of material out here in this fluid. If you add something called PEG, I forget what that stands for at the moment, that will tend to suck the water back out by osmotic pressure. And you can adjust this PEG concentration, and you can look at how much the pressure is, the osmotic pressure that's in the pressure difference really that's in the cartilage. So what you're going to do is the problem asks you to imagine you're doing an experiment where you're adjusting the concentration of this PEG, and you're asked to do basically analyze some data. The problem walks you through it. And eventually, if you get this concentration high enough, it'll be as high or a higher osmotic pressure than the cartilage, and there will no longer be water held in there, and this collagen will all sort of collapse, and that's called going limp. So you're going to look at how you can make the cartilage be sort of expanded and then go limp. And that's problem 5.8. It sounds complicated, but it's really kind of step-by-step going through, tells you exactly what to do. So, and problem, let's see, the only other problem, 15 and 16, we'll talk a little bit maybe at the end of class today. That's just another example of osmotic pressure. Okay, now, on to our main topic for the day. And this is countercurrent properties in fluid flow and in heat transfer, basically. So, this all resolved. We're going to spend probably most of the class period on problem 5.19. So, problem 5.19 says, countercurrent model applies to the transport of heat as well as particles. Well, in the book, it analyzed the transport of particles, so in the homework problem there, I was looking at transport of heat. Consider a countercurrent heat exchanger, which represents the arrangement of blood vessels in the flipper of a whale, or as we'll see in the foot of a duck. So we're going to go through this and kind of analyze it. If you're interested in these kind of effects, funny effects with animals and funny physiological developments, I recommend this book, How Animals Work by Knut Schmidt-Nelson. And it's another book that's not required reading, but is interesting if you're interested in physiology. Okay, so let us see what we got here. Let's imagine you have a lake on a cold winter day. Here's the water in the lake, here's the air above the lake. And what you have in this lake is you have a duck. Oh, here's your duck. Okay? And the duck is a warm-blooded animal. It's got a high temperature inside, probably close to 37. I'm not sure exactly what the temperature is for birds, but it's probably around 37. And ordinarily this duck would be fairly able to exist. It's up here, most of it's in the air, which is a little bit exposed to water. It's got feathers for insulation. So the duck could thrive just fine, except that it's got this foot that's sticking down into the cold water. And that foot is just like a big heat sink. And if this water is near freezing, you're going to lose a lot of heat out through that foot. So the goal then is to figure out how to avoid losing all the heat to the cold surrounding water through the foot. And here's the way the duck does it. It sets up a countercurrent heat exchanger. So let's look a little more in detail at what this means. Here's the duck more schematically, the hot temperature. Its artery in the foot comes down here like this. So that's the artery, which is carrying blood down. It's carrying warm blood down into the foot. And then it goes through a capillary down here. And then it takes its cold blood back up in the vein. And we're going to try and make a model for this. So we're going to start with just giving some coordinate system. We're going to take X is 0 right here where it enters the body, and X is L, we're down by the capillary, so X is going down in this direction. And we need to analyze this, and we need to basically derive differential equations. So, but before we do that, let's think a little bit about what the boundary conditions are going to be. The blood, the temperature of the blood as it enters this artery here is going to be the same temperature as the body. So, I will write that as, we're going to keep track of the arterial and the venous blood temperatures. So TA at X equal to 0 is T hot. That's our assumption, that's the boundary condition. So the arterial blood comes down, and then as it goes to the capillary, it's very easy to exchange heat in the capillaries. So by the time it gets to the end of the vein here, we're going to assume that it has cooled off down to the temperature of the surrounding water. So the temperature of the vein at X equals to L is going to be T cold. And those are our boundary conditions for these variables. So we're basically trying to find TA of x and TV of x, both as a function of x, and we know that they are at the ends. So let us go through and see if we can derive a differential equation that describes, we're going to need two differential equations, one for the arterial temperature and one for the venous temperature. So first of all, we're going to assume that in the artery, the way you transport heat down along the artery is going to be purely by convection. There's not going to be any diffusion of heat along the artery. So you can talk about the Peclet number and the contest between diffusion and convection. Well, in the artery itself, convection wins. So how did we write the current density? J, which in our case is going to be the amount of heat per unit area per unit time. How are we going to write that as a function of convection? Well, we know the blood's coming down here. We're going to say it comes with a speed v. So how is this current density related to v? If you didn't have any motion, there wouldn't be any current density. So it's going to be proportional. Remember when we talked about convection of molecules, we just wrote it as v times the concentration. Well, now we're going to talk about it as conduction of heat. We're going to write it as v times the concentration of heat, which really is a thermal energy density. Thermal energy density. Okay, so that's going to be the amount of heat per unit volume, and this is the speed, meters per second. Now, how can we write the thermal energy? How much thermal energy is there? Well, let's try to relate that to the heat capacity. Basically, the amount of energy is heat capacity times the amount of times the temperature. So I can write this. I'll keep the V, and now I'll write heat capacity times temperature. But I want to use it really per unit volume. I'm going to write it as specific heat, C star, and then that's per unit mass. So we have to multiply the mass, but the thing is already per unit volume, so we really need the mass per unit volume, which is the density. So the product of these two would then be the specific heat per unit volume, and then the temperature, T. And that really gives us our thermal energy density for moving heat up and down here. And we have two of them. We have arterial, which is V C star rho arterial temperature. And in that case, we have that going down, we're going to take as positive. We just have to get our sign convention, because that's the natural direction that the blood's flowing. And we have the venous, which is V C star rho TV. And in that case, we're going to take up as positive, because that's the natural direction of the flow. All right, so we have this. Now, what else do we have to have in order to understand the differential equation? We need to get some sort of continuity relationship. This is the same way we derived a lot of the equations before. First, we get some relationship expressing what the current density is, basically, and then we have a relationship giving you the current, how the current density changes in space by continuity. So let's look at the artery. And so we're going to take a piece of the artery, and we're going to look at it. We're going to call this piece a distance delta x. So that means that this spot here will be x, and this spot will be x plus delta x. And we want to keep track of how heat moves in and out of this little volume. So this is an expanded version of right along here. Well, how can heat? Heat can go in from the top, because you got a J, A coming down here. So what would that be? That would be how much heat per unit time, basically. What's the power going into this volume? Well, it's JA at point X times the area. Because then you get heat per second, or you can get power. You can also have heat coming out. JA down here, and that's coming out, so it's a minus. And then it's x plus delta x and A. But there's one other thing heat can do, and this is the new piece that we haven't talked about yet. We're going to assume that the artery and vein can exchange heat. That's the essence of the countercurrent technique. If the artery and vein couldn't exchange heat, then JA with here would have to equal JA there, and all you'd have is just be carrying the heat down the artery. But in our case, we can get something, I'll call it a JAV, which is the heat exchange. It's coming out, so just like this one, we're going to give it a minus sign, because it's coming out of this region, and it's JAV times the area. Area is a little tricky. It's got delta x. It's the area of this wall here. So it'd be delta x times really the depth into the board, which we will call D. D is the depth into the board, because this thing's a 3D object. So it's this times that. That's the area that it's going to exchange with the vein. And you put all that together, and that energy is conserved. That has to be 0. Okay, now give me a little help here. What's the typical thing we do at this point? Somebody help me out. Pardon? Okay, oh, you could factor the A out, but oftentimes we like to, let me put it this way. What can we do to kind of isolate just the JAV? We could divide by delta x times D. Because you really want to divide by delta x, because you're going to try and make this a derivative. Let's go ahead and divide by delta x and D. Okay, we'll factor out the A like you said. And we're going to divide through by delta x and D. I'll put the D out here. I'm going to bring a minus sign also. So what do we got left? We got this JA. We factored out the A. We factored out the minus sign. So we got JA x plus delta x. And we still have a delta x. Then we have another term here, which now since we factored out a minus sign becomes negative. JA of x.
That's some like formal differential equation.
It's going to become a differential equation when we take delta x going to 0. It's not quite a differential equation yet. And what's left over here, well, we have moved the JA to the other side, AV, and we already divided by delta x and D, so it just looks like that. Now, we'll take the limit as delta x goes to 0. And what we'll get is this thing, which is a derivative, dJA dx. And I want to move this now all to the other side. So I'll move the minus D over A JAV. That is really a continuity equation relating the current densities. Okay, so let's try it in the vein. The vein is going to be very similar. So we'll just show the vein here. A little region in the vein, again, delta x. And it's going to have, the J's are positive going up in the vein, so it will have a J down here, JV, coming in, and that will be at x plus delta x, and it'll have a J. Really, it's going to be JV up here, and it also has this, any heat that comes out of the artery has to go into the vein, JAV. So, why don't you, I'm going to give you 2 or 3 minutes. I want you to derive a similar type of equation, very similar to this, but for JV. So why don't you give that a try on your paper, and then we'll, after a couple minutes, we'll compare notes and see how you do. Yes.
The subscripts A, B for the plus, is that like the key to the artery of the vein?
Yeah, that's going to be represent the flow from the artery through the vein is going to be the positive direction. Yes.
What's your heat flow out the arteries that came to the environment, the cold water?
Well, there's going to be heat flow into the environment down here, the capillaries. We're going to assume that the only place that happens is at the capillaries. Basically, we're going to assume that the artery and the vein are fairly well thermally insulated, except they can exchange with each other, which means they have to be in close contact. But when you get down to the capillary, and that's where you're going to get all the exchange with the lake itself. So there's some assumptions here. Okay, anybody have a differential equation? Yeah.
D over A, JAB equals DJB over DX. Yeah, so that equals D over A.
D over A.
Yeah, JAB.
Is that what everybody got? Or anybody get anything different? When I do it, I still get a minus sign in here. I still get a minus sign because you're going to have, basically this is going to be JV at x plus delta x, and this is going to be minus JV at x. So that's going to give you the derivative, and this is going to be coming in, so you're going to get a plus JAV. Move it to the other side, it's going to give you a minus still. So
as we're defining x is the bottom portion, not as the top.
The x is still going to have this as x plus delta x, and this is still going to be x. So x is still defined as going down.
Okay.
So I'll just say that real quickly here. JV at x, and that's coming out, so that's a minus times a, and coming in is JV x plus delta x. That's times a, that's this one. And coming in is also plus JAV d delta x. And all that has to be 0. And so then I'll multiply through by the delta x, or divide by the delta x. This will become JV dx. I'll move this to the other side. And now why am I looking like I'm... Okay, I screwed up, so I can see why you guys get the signs wrong too. Coming in, that's JV, and that's okay. This is plus JAV. Everything's good. I move it to the other side. It becomes minus JAV, and I divide it by delta x, and I divide it by d. So, and I factored the a out. So this becomes d over a JAV. So it's exactly the same differential equation as for JA. All right, so we're almost there. All we need now is an expression for this coupling term, because we haven't really talked about the coupling term. So I'm going to need, well, there's enough space here. I will write JAV is going to be, okay, it's going to depend, first of all, on the temperature difference between the artery and the vein. That's what's driving the exchange of energy between the two. They're at the same temperature. So this is really going to be like a diffusion term. But instead of being a gradient, it's going to be the temperature difference that's going to drive it. And that's going to depend on some constant which tells you how intimately these are connected, how good a thermal contact they're in. It's going to depend on this distance between the two, E, and in fact it's going to be, the smaller E is, the larger you're going to transfer the heat. And then we said it depends on your TA minus TV. So that's going to be our assumption for how heat's exchanged. So we're almost there. We're going to have to put all this together. Problem is I'm running out of board space. So before I start erasing things, let me ask if there's any questions on any of this so far. Now, I'm going to erase this derivation, but keep the stuff in the boxes. That'll give us some space. So, here goes the artery and the vein, and then all of this. C goes to L. I probably shouldn't have erased that. Now, what we're going to do is we're going to put everything together. Here's our JA, and for JA, we're going to use this expression. And B, C star, and rho are constants. And now you have a derivative of JA, so that means a derivative of the temperature in the artery. Then equal minus D over A times JAV, which is this thing. Kappa over E TA minus TV. Then you're going to do exactly the same thing for this equation. JV is going to be this. So V C star rho dTV dx equals minus D over A times JAV, which is that, kappa E TA minus TV. Now, this isn't too complicated, but it's a little messy. So what I'm going to do is I'm going to divide both sides by V C star rho. So I'll get dTA dx equals, and I'm going to get a V C star rho down here, and you have this D kappa AS, whole bunch of constants. I'm going to absorb all those constants into just one number. So I'll keep the minus sign, TA minus TV over lambda, where lambda now has to be what? It's down here, so it's AE, and these things came down here, VC star rho, and these become the denominator over D kappa. It's got to have units of length by the way we constructed this. This is a derivative, temperature with respect to distance, so this has to be temperature over distance. Not obvious from that big complicated mess that that's what the units are, but it is. And the other equation is going to be dTV dx is equal to minus TA minus TV over lambda. And what we get are two equations in two unknowns, in two variables, so it's really a coupled pair of differential equations. So this is the kind of thing you often find when you're making mathematical models. Instead of getting one differential equation for one variable, you get two differential equations or a system of differential equations for a bunch of different variables. So our variables are the temperature in the artery and the temperature in the vein, and it's a function of x, so I don't have to use partial derivatives, there's no time. This is a steady state model, by the way. I didn't say that explicitly, but it is. And it involves one parameter, lambda, which involves a whole bunch of physical parameters. All right. So what we've done is we started with the physics, and we came down and we came up with a mathematical expression. Yes?
Why would the expressions be the same if you're going from arteries and veins versus it's the same value?
It is the same, and we're going to take advantage of that here in just a second. Why it is? Well, part of the reason is that any energy that comes out of the artery, we're assuming is going into the vein, so they're tightly coupled. There's no, like was mentioned earlier, we're assuming there's no energy loss out here to the rest of the foot. So that sort of, and since the physics is very similar in the two, that sort of implies that it's very likely you're going to have very similar equations. Well, it turns out, just from the way we took all our sign conventions and everything, that they're identical. Okay, so what we've done is we've gone from the physics and we derived some math. Now we're going to solve these math equations, and then we'll go back and we'll try to understand what they're telling us physically. So physics, math, physics. We've done one of those steps. Let's do the rest of it. So I'm going to have to get a bunch of board space again, and that means I'm going to have to erase a bunch of stuff. So last chance to ask about some of these equations before I erase them. Okay, and I'm going to start erasing all of this. And the only thing I'm going to keep, and I'm going to rewrite it over here in the corner, just so we have it. So I'm going to rewrite these two equations. Minus TA minus TB over lambda, and dTB dx is minus TA minus TB over lambda. Okay, so now I can do everything else. Maybe I'll keep the picture. Let's see. Okay. So, how are we going to solve this? Well, first I'd like to do is take advantage. You had pointed out that these two equations look the same. So let's just look what happens if you subtract the two. Because since the right-hand sides are the same, you're going to get that dTA dx minus dTB dx is equal to 0, which means TA minus TB is equal to 0. What that says is that we don't know what the temperature is yet in the artery and the vein, but whatever that temperature is, the temperature difference is always going to be the same between the artery and the vein. They may both be changing temperature, but their temperature difference is constant. So we've already learned something, even though we haven't really solved the equations yet. So I guess I'll just write it this way. dA, if the derivative is 0, that means the temperature difference is a constant. And we might call that delta T. And it's not a function of x. It's just going to be a temperature difference. Now, what's my favorite way to solve these differential equations? We're going to guess and we're going to check. So, now this is a case where it's not exactly obvious what you want to guess. Because if I ignored this TB term, what would you expect for a solution for TA? You'd get, pardon? No. This equation, the derivative with respect to x is proportional to the TA itself. I would just give you an exponential. So you might be tempted to guess an exponential. And you could guess the exponential, but it turns out that in this problem, you're not going to need it. And the only way to really understand that is to try a big guess that has a whole bunch of terms, and you find out and discover that the exponential terms go to 0. I'm just going to state that as a decree. We don't need exponential terms, although it sure looks like they might appear. So what else is left? What kind of functions, if you take the derivative, would give you, well, this thing is going to be a constant. So what would give you a constant if you took the derivative of it?
Sorry, no coaching.
No.
All right.
If it was x, if it was linear in x, then you take the derivative of it, you're getting a constant, and that has some potential. And a constant itself, if you took the derivative of it, would give you the 0, so it wouldn't screw things up. So let's just use, as our guess, TA is going to be AX plus B, and TB is going to be CX plus D. Now, what do we do with these? What do we do with the guess once we have the guess? Plug them into the differential equation and see what the differential equation tells us. So we're going to plug this into here. And we're going to plug both of these in for TA and TV. So what's the derivative of this? A. That's equals a minus 1 over lambda. And now I have to take TA minus TV. So I just write this down. AX plus B minus CX plus D. This has to be true at all x values. So, I guess there's a bracket at the end of this. That has to be true at all x, not just any one x. So what's that say about the relationship between these parameters? Let's look at just the linear terms in x. There's only 2 of them. There's no linear term over here. This has AX minus CX. And that has to be 0 because there's nothing here. So what's that say about A and C? They're the same. So we know, we found out that A equals C from this analysis. And that leaves A, or the constant terms, is minus, and this is a B, and this is a minus D, and you have a lambda. And we know that A has to equal B minus D over lambda. It's also what C is. Well, if you plug this equation into this term, you get exactly the same thing. You get C on this side. This side would be identical, but we already know A and C are the same. So you really get this one equation relating A and B and D, and you get this expression that A and C are the same. So basically, if we know what B and D are, we could then get A, and we know also C. So we got 2 of our 4 unknowns we've basically solved for, but we still don't know B and D. So everybody with me? What do we do to get B and D? Boundary conditions. Okay. So let's go back to TA. At x equals to 0 is equal to T hot. So TA is this. At x equals 0, it's going to be T hot. At x equals to 0, this term goes away and you just get B. Well, we immediately found what B is. Great. So B is T hot. Now, let's see what the other boundary condition is not going to be quite so easy. TV is equal to T cold equals TV is CX plus D, and we're evaluating it at x equals to L. So that's CL plus D. All right, so now we have these 2 expressions from our boundary conditions. But we know what C is. C is A, and A is this. So we know that this is equal to minus B minus D over lambda L plus D is going to be T cold. So we know this, and we know this. Just to point out, all I did here is I said C has to be the same as A, and we already know that A is this quantity. So we basically have 2 equations and 2 unknowns. One of them is real easy because we already solved it. That's B. We could plug in T hot into here and solve this for D. I will let you do that after class. but I will write down what I get for D. So all I'm doing is solving this equation for D using B as T hat. I will get D is equal to lambda T cold plus, whoops, there's these. That is plus L T hat over lambda plus L. That's D. That's B. Once you get D and B, you can get A and C. And that's just plugging B and D into there. And so A, which is also C, is, I will let you also go through and do this algebra. It basically matters of taking B minus this thing, putting it over a common denominator, so you end up getting a common denominator of lambda plus L. So that's going to give you a T hat times lambda and plus a T hat times L for the common denominator. And when you subtract off D, you're going to get the T hats times L's are going to cancel. And it turns out pretty simple. It becomes minus T hot minus T cold over lambda plus L. And that's what A and C are. So we know A, C, B, and D, we've solved the entire problem. And we can write down our solutions now. We can write down our TA of x is equal to AX plus B. And A is minus T hot minus T cold over lambda plus L. That's a plus times X plus B, which is T hot. And then we can write PV of X is exactly the same. A and C are the same, so this term's exactly the same. T hot minus T cold over lambda plus L X. And D is a little more complicated. Plus lambda T cold plus L T hot over lambda plus L. And that is our solution. Now, we know that TA minus TV is supposed to be a constant, which we call delta X. So that means we know what delta X is, delta T is. The difference between these two, this term just goes away. That was kind of by design. And you get T hot minus lambda T cold plus L T hot over lambda plus L. And again, what can make this a little nicer? What can you do to make this look a little neater? To simplify it. What's the problem with this expression that makes it look ugly? I know that's somewhat subjective. I want this thing over a common denominator. Because having this denominator, let's put the whole thing over a common denominator. So you're going to have the whole thing over lambda plus L, which means you get a lambda T hot plus L T hot, because you had to multiply top and bottom by lambda plus L, minus lambda T cold, and then this minus sign carries through, minus L T hot, and again, these cancel. So delta T does come out to be somewhat nicer looking. It's got a lambda out front, a T hot minus T cold over lambda plus L. That's that temperature difference that we were wondering about. Okay. Let's take a break for a second. That's the math. We took the physics, we developed the equations, we took the equations and we solved them mathematically. Let's go back and understand what's happening physically to this problem. So I'm going to erase a bunch more stuff. Anybody have any questions before I erase? Okay. Then we'll get rid of all this. Actually, we'll get rid of all of this. Then we'll get rid of all this. We'll keep that stuff over there. Now, first of all, where is the heat loss to the lake? We assume that there's no heat loss out here going to the other tissue. All the heat loss goes to the lake here. So the heat loss is going to depend on what the temperature of the vein or the artery is down here, and the temperature of the vein here, which we know is T cold. So really, the heat loss to the lake is this delta T. It is because delta T is really the temperature difference at anywhere, so it would include x equals to L. That temperature difference is the same everywhere, so that's the temperature difference between the artery and the vein here. So it's temperature across the capillary. That's what gets lost to the lake. So you want to minimize this. Temperature, heat that goes into the lake is just lost. Lost to the animal. The animal will have to make it up through warming, its own metabolism. So you want to keep this delta T small. So let's look at two cases. Let's see if L is less than lambda. So you really have two parameters here. L, which is the length of this, and lambda, which is some collection of constants. So what does delta T become if L is a lot smaller than lambda? What do you get for delta T in that limit? You just get T hot minus T cold. Because L is small, so you get lambda over lambda, which is 1. So what that says is, in this case, this is bad news. Because you're losing all your, this is a large temperature drop. This is the largest temperature drop you could have. It's the entire temperature drop from hot to cold occurs through the capillary, and you're losing a lot of heat to the lake. But we can look at case 2, where L is much greater than lambda. And what's the temperature drop in this case? If L is much greater than lambda. Okay, ignore this lambda to L. It just becomes lambda over L times that temperature difference. But lambda over L by design is small. So that says this is a lot smaller than T hot minus T cold. So what we want is we want to make this lambda small. Remember, lambda is a collection of parameters. If we can make lambda small, we can minimize the heat loss to the lake, and that way we can keep from freezing to death. So, what do these look like if we plot them? Here's going to be x, 0 to L. And here's going to be T, this is T hot, and this is T cold. And we're going to plot both artery and vein. Well, we know a couple things. We know the artery has to reach T hot at x equals to 0. This is the artery coming right out of the body. It's nice warm temperature. We know that the vein is going to be equal to T cold here at x equals to L. We know that these two differ by delta T, and we know that they're linear functions. So we're going to get two parallel lines because their difference is a constant. And so they're going to look something like this. This is going to be, those are meant to be parallel. Not such a good job, but this is TA and this is TV. So what happens is the arterial blood gets cooler as it goes down. Why does it get cooler? it's in thermal contact with this cold blood in the vein. So it pre-cools the arterial blood as it goes down. It pre-cools it by thermal contact with the vein. And the vein also changes its temperature. And starting from a really cold temperature, and now as we go back up, we're kind of going in this direction, it gets warmed up. How does it get warmed up? It gets warmed up by the warm blood in the artery being next to it. So the whole idea of the countercurrent process is you pre-cool the arterial blood by pre-warming the venous blood. So you get down here and the temperature difference is real small, but you haven't lost all this heat out to the lake. You lost the heat by exchanging it between artery and vein. No big deal. It's just moving it around one part or another, one piece of blood to another piece of blood. So when you get up here at the top, your temperature difference is still small. It's this delta T. And that means the blood going into the body is, see, this is going to be hot blood right here. But this is going to be cool blood here. And this is going to be cold blood here. There's going to be a little bit of heat loss. And this is going to be warmed up back, so it's warm blood. So all you got to do is take warm blood into the body and then do a little metabolism to warm it up all the way to hot temperature. But if you can make that delta T small, you can get blood that's almost back at body temperature. Yeah.
So we minimize how much heat is lost in the lake, but what if the temperature between the lake and the lake is so great? Like how do we don't have frostbite or like delta T?
Well, that's a good question. The flaw in this whole plan is that the leg gets really cold down at the bottom. So if you were relying on, say, the toes in that foot to be able to do a lot of fancy manipulations, you might get frostbite. But the duck basically has a webbed foot down there, and its main goal is to just sort of use this paddle. So apparently the duck can live with a really cold foot. That's what they got to live with. That's the price you pay to not lose all the heat. So you can't have everything. Well, one thing you could do is completely thermally cover up the foot. You could put the entire foot and leg into some thermal wrap. But apparently that's not good for, I guess, the fluid dynamics of the duck or for swimming or something. That duck has not chosen to do that. It's chosen another trick, which is this countercurrent heat exchange. But it's a good point. So, let me just show you case one here, where the two temperatures were, delta T was almost constant. That really looks like almost like this. This is the large delta T. There's very little drop. That's case one. This is bad. Case two, hot, cold, is when you have almost a complete temperature drop. So that this delta T is very small, and then you have essentially the temperature all the way down to almost to the temperature of the lake by the time it hits the capillaries. That's good, at least for heat loss into the lake. Okay, there's one more thing I want to talk about with this. And we'll get some space over here. Really what's important is the length of the leg, which is probably fixed by what it needs for its swimming, versus lambda. Lambda you can play with. Lambda evolution can play with to try to adjust and make this a good countercurrent heat exchanger. So we got to remember what lambda was. Lambda was V C star rho times A times E over D kappa. All right, so you can't do much with C star and rho. That's just the properties of water or blood, which are basically the same. The area you could play with, but you got to have enough blood. The reason why you have any blood coming down here is to keep this tissue from dying. You got to have enough blood down there to keep it from dying. And kappa you could play with a little bit as far as thermal contact, but the main parameters you're going to play with are E and D. These are two distances, so let's remember what those were. Here's the system. And this distance here is E. What it says is you want E very close. So what you want is you want to bring the artery down and have a really close contact with the vein so that there's hardly any difference. They're very close to each other. You can make this heat transfer very easily. That's what lambda being small means, really means good heat transfer between the two. And you want D. You want D to be big. So you want D, if you remember, is the distance back in this direction into the board. Now, but you want A small. So let's look at these from a top view. So this is a side view. Let's look at what these should look like from a top view, looking down. So we're looking down. I mean, if you think it would look like this if you were looking from a top view down. But actually what you want is you want something that looks like this from the top view. You want to make it very well coupled. So now what you want is this distance here is E. That's the distance between them. You want to minimize that. You want D, which is really this. D in this case is sort of this size. That's the size that was into the board here. You want that big so that there's lots of area to interact and exchange heat. But you wanted A small in order to keep the lambda small. So that means you don't want this cross-sectional area of any one vessel. So you want some vessels that look something like this in cross-section and coming down here. That is what you end up getting in a lot of these countercurrent heat exchangers. You get something like this, or in other systems, you end up getting the artery here, and you end up getting veins, maybe several of them, just surrounding it. I mean, there's various ways you can set this system up, but you want to have large surface for heat transfer with fairly small surface for heat going up and down. Okay, now there's one hitch in this, and that is, what's blood for? Blood, the reason we have blood is to bring oxygen down to the tissue. Now, if this is such tight, intimate contact to exchange heat, why don't you exchange oxygen? Why don't you end up losing all your oxygen from your high concentration arterial blood into your venous blood, so that not only do you pre-cool the blood, you deoxygenate it, and then this dies from ischemia. Okay, so what we mean is we have to talk about we have to compare basically how well oxygen is going to diffuse, and we're going to have to compare that to how well heat's going to diffuse. And we're back to what we talked about in the previous chapter, the Lewis number, which is really a comparison of these two. And it turns out that heat will transfer much better than oxygen. That's just from the laws of physics. You saw it when we looked at the Lewis number. The Lewis number came out so heat in both air and water transferred much better than did oxygen. So you can set the system up where there's just enough time and just enough heat transfer with fairly minimal oxygen transfer. And that's why it works. If it was the opposite and oxygen diffused better than heat, you'd be lost. By the time you saved the heat, you'd have lost all your oxygen and the blood wouldn't have any purpose anymore because it wouldn't be delivering oxygen to your foot. So you see some of these concepts that we talked about earlier come back in this analysis. So that is the foot of the duck. Are there any questions about that? Yes?
For between the artery and the vein,
Yeah.
do you use just the total change in distance, or would you need to calculate all the bends and curves between the artery and the vein?
Well, see, it's a little tricky, but you're basically this E is this distance between them, so that would be this. And the D, probably you would want to calculate it in a tortuous way. So probably I'm not correct in saying D is just this. D is really this path length, which can be much higher if you do make it tortuous like that. So that's a good point. That's why you do the tortuosity, to increase that D. So you change, which would come back and increase D, decrease lambda, and make things nicer. Okay. Let me show you one other example where this occurs. We looked at transfer of heat. You can also get transfer of particles, and we're just going to talk about this qualitatively. But this is the gills of a fish. There's two ways to set up the gills of a fish. So here's the artery, and the vein, and the capillary from the fish. And it's got blood flowing in this direction. And here's the surface of the gill, and here's the seawater. Now, you could have the seawater come through this direction. So, if you in the same direction as the blood, you'd have a lot of oxygen here. The oxygen would get absorbed by the artery, and just a little bit of oxygen there. That's not countercurrent. That's the same way. If you did analyze this, and again, we're going to skip it because we don't have time, you would find that in this case, you do get those exponentials. You'd be looking at X, and you'd be looking at oxygen concentration. And you'd find that the oxygen concentration over here in the blood was, this would be the blood, this would be the seawater. You start off with arterial blood. Did I get that right? This is actually the vein. No, that is right. This is the arterial. The arterial blood. This is where you're picking up oxygen. It's not where you're delivering it to tissue. So you're picking up oxygen, and you'd have almost no oxygen content here. This is like in our lungs. And you have a large oxygen here, and as it went by, you'd end up down here where they have the vein and the seawater would have about the same oxygen concentration. It wouldn't be a real effective way to transfer oxygen because you deplete the oxygen over here, and you'd end up with only about half the oxygen in the blood. But if you design this another way, the artery and the vein look exactly the same. And this is the capillary. And now you flush the oxygen over here. So it just depends on how you bring the seawater in by the gill. Now you have a countercurrent system. And now you can design this system. So big oxygen, little oxygen. And you can design this system in this countercurrent way with like we did with the heat. And what you're finding is you have a lot of oxygen over here, and you'd still be transferring it to the vein here. You'd have still a little bit of oxygen, but you'd have no oxygen here. You can maximize the total transfer of oxygen to the gill. I admit, it's not obvious from this analysis, but you would end up getting, at the end, a much better transfer of oxygen to the gill using this countercurrent system. It's similar to the heat system we looked at. So it's not just in duck feet that you see this. Okay, we are about out of time, but we will move on next class and start on chapter 6. And if you haven't handed in your homework, put it in the envelope right there on your way out.